Hello and welcome to this series called Pin for Wearables. So, this is a mini series where we will be presenting how to use a physics informed neural network to solve a real world problem in the motion tracking space, which involves industry grade sensor data. So, the problem we'll be focusing on is that of estimating orientation from IMU sensors. And this is an open ended research problem and has applications in a wide range of domains, ranging from sports to biomechanics to robotics and even self driving cars. So, this project was done by myself as part of a technical interview for a research engineer position at a top level consumer tech company in the Netherlands. So I am Vivek. I hold a BSMS in physics from ISER Kolkata, India's premier science institute. I've also worked as a software developer at TrackMan, which is the world's leading company in golf motion tracking, as part of the research and development team. I'm currently pursuing a PhD in mechanical engineering in the US at the University of Iowa, and I'm interested in scientific machine learning. So, in this mini series, before we jump to the technical stuff, in this introductory video, we'll be sort of discussing the problem at hand, how pins actually fit into the bigger picture for this problem statement, and how this mini series might be the right fit for you. So, let's actually start discussing the mini series being a right fit for you so that you'll be able to gauge if you want to go ahead and participate in this mini series, and if you can gain something out of it. So let's first discuss that. Okay, so is this mini series the right fit for you? If you come from a wearables, biomechanics, sports engineering, robotics, navigation, or controls theory background, and you want to get into this exciting world of pins, and you've actually been trying to find material that's a right fit. You have all the domain expertise, you know the math, you know Python, but you were looking at like resources to learn JAX or PyTorch and code up pins. This mini series might be a great fit for you. Another case might be that you come from a traditional physics or engineering background and you wanted to get into neural nets or pins. Pins is a nice bridge going from physics or engineering to AI, ML, neural networks. So you wanted to get into this through this like very unique use case of motion tracking. This might be the right video series for you. Um, Another thing I can think about is that you're a hands-on learner as opposed to someone who reads a lot of research papers and is very theoretically oriented. You prefer a hands-on approach where you actually start coding up workflows and getting a sense of what's happening and looking at real-world problems. Maybe you learn that way, and that sort of helps you build the intuition and feel you need to then dive deeper into like theoretical aspects and the actual meat of the problem. So you might be a hands-on learner. The fourth bullet point I can think about is that you actually are in this space of AI, ML, neural networks, SciML. You might be very specialized in SciML and know Julia, or you might have been involved in like model-based deep learning and you've been using PyTorch and TensorFlow for a long time, and you actually want to learn JAX, but you just aren't able to find a resource which can get you like up to speed. So you need a quick start in JAX. So the part one video of this mini series will be very helpful for you. That's another thing I can think about. A fifth point might be that you're actually involved in the process of writing scientific grants, or you might be actually preparing for like coding interviews for research positions where they give you take home assignments. And with these sort of scenarios, there's always the challenge of having limited time and maybe limited computational resources, and you have to know how to scope out a problem, how to make critical decisions whether I should do this or not do this, and actually get something which works, get the entire pipeline going, which demonstrates that you actually know this technique. So this might be helpful for you. Then we are planning on having a Virat Kohli thumbnail for this because this is about pin for wearables, which relates to sports. And if you just like watching videos with a Virat Kohli thumbnail, this might be for you. Then, one final point I can think about on my end is that you're interested in sports and you're very curious about how physics, AI, and sports tie together. So, physics and AI tie together through pins, and pins and sports will come together in this mini series called Pin for Wearables. So if you like sports and you're wondering about, oh, I like physics, I like AI, I like sports, I want to do a cool project which combines all of these aspects, this might be a great fit for you. And then you can fill out the last bullet point. I'm sure there are things I haven't thought about, but you might figure it out. So I would say just sort of go through this mini series and have an open mind, and you might have your own reasons to do it. And that's why you can fill this last bullet out. So that being said, having sort of covered the motivation and discuss if this mini series is the right fit for you, the next thing I want to share with you is a little bit about this company that I interviewed for. This is like a major player in the motion tracking space, and they have been tackling problems ranging from sports, biomechanics, um, just building wearable, high tech wearable sensors for research labs, robotics, self-driving cars. So they have really like done a deep dive into this motion tracking space. They've created the best sensors and they have tackled like a wide range of problems. Oh yes, even they also work with digital artists, and I think they're involved in movie creations and Hollywood and animations. So this is like a really fun company which sort of uses motion tracking for a wide range of applications, which is why I found it so exciting, because I know a lot about sports and I'm interested in that as well as physics, but I don't know much about robotics or self driving cars. So, this seems like a company where you can get to do a wide range of exciting projects and expand your knowledge. And this is the world's leading company for creating industry grade, high tech IMU sensors. And IMU sensors are also used by the military and they're also used by the navigation industry for navigating aircraft. So there's also like a defense application. So, enough of me talking. I'd like to share a fun video about this company with you.
Everything moves. In the heavens, on the earth, inside our bodies, even our states of mind. Everything. But only when movement is measured in ever finer ways, then analyzed to reveal trends and yield insights, is there meaning. Welcome to Movella. By digitizing movement to create positive change, we're bringing meaning to movement. In entertainment, empowering digital artists to unleash their creativity using the most advanced and easy-to-use motion capture technology. In sports, providing teams and athletes the tools and insights to push beyond their limits. In health, delivering technology-enabled insights that remove barriers to human motion. And in industries, by providing superior positioning and orientation systems within complex commercial environments. New applications that move humanity forward are discovered virtually every day, all thanks to Movella, bringing meaning to movement.
So, now with that really great introduction aside, the next thing that we need to understand is how pins fits into the bigger picture. And with that comes embedded systems and our problem statement. So we do need to understand a little bit about what embedded systems are. What does the term embedded systems mean? Look at a few examples and also discuss a problem statement, because that will provide clarity as to what problem we are actually trying to tackle with pins, and what is the actual system that we're dealing with and how does it fit into the big picture. So the next thing we'd like to do is that I'd like to actually again show you a really nice snippet from a great video by this channel called Engineering Insiders, which discusses a bit about embedded systems. So let's get to that.
System Freaking cool is what it is. No, but seriously, embedded systems are a culmination of hardware and software designed for a vast array of physical applications. This could be a standalone product, like a graphing calculator, or part of a larger system, like the navigation and guidance methods for a satellite orbiting Earth. We have another embedded engineering video that details this well, but for now, let's take a look at that satellite as an example. The onboard embedded system processes data from sensors like gyroscopes and accelerometers to determine the satellite's position and orientation. From there, our embedded system sends signals to stimulate actuators like magnetic torquers and thrusters to correct its orientations and stay on path. In other words, the entire navigation system is embedded right into the satellite. But these systems aren't just found out in outer space. You can find them while checking out at your neighborhood Chipotle, driving your food home, and loading up the most recent Engineering Insiders video while you eat. Engineering the
So I hope you sort of get a sense of what embedded systems are. They're just systems, like tiny systems built into some device specific to that device. And in our case, we have a system navigating or moving through space. And there's a sensor, like a tiny sensor embedded into that system. And that system actually gives us data, and we need to create some insight for data. And we want to use pins to do that. So how pins comes in, or what the actual mechanics of the pins, is something that we'll get to later on. But the idea is we need some sort of technique to process that data and gain insights for a system which is a sensor placed on an object which is moving through space. So now that we have a sense of that, next thing I'd like to do is show a great example of an embedded system, and we'll use that to relate that to our IMU sensor problem statement. So, okay. The next thing is having a look at another great video by this channel, Engineering Insiders, and then relating it to our IMU sensor problem statement.
Just as promised, we'll be investigating the fascinating details of a GoPro digital camera to carry us through the nuances of an embedded engineering design. We've simplified the details just a touch for the sake of the video, but all the core concepts hold true. Without further ado, let's get right into it. It all started with GoPro founder and California native Nick Woodman hatching a brilliant idea that would eventually cement the dominance of embedded systems in the 21st century. He was simply looking for a better way to film him and his friends surfing, speculating that there would be a ton of others like them with the need for a small but powerful digital camera. This idea perfectly set the stage for a world-class, multi-million-dollar embedded system design. They went to the drawing board and decided upon 3 major parts of the camera to start designing, which are consequently the 3 areas of focus for every embedded design. So make sure you're paying attention here. They are the hardware that can film and store quality videos, the software that controls the process and interfaces with users, and the compact, rugged casing to protect the technology inside. But what is the technology inside? What are the embedded engineers actually designing? Okay, let's explore that. Starting with the most obvious part of the camera, we got the lens. The engineers took their time choosing this part, as it's the single most important input for the camera. The light reflected off the subject to be stored as a video. Once this light is herded into the body of the camera, it needs to be transformed into an electrical signal so our embedded technologies can manipulate and store it. This transformation from light to an electrical signal is accomplished with a CCD, or charge-coupled device. Basically, this CCD has an entire field of discrete points that light hits, and each point emits a current proportional to how strong the incident light was. The embedded engineers chose the single best CCD for the design, as there's simply no room for inefficiencies in this small camera. The electrical signal from the CCD is routed through an analog to digital converter so that the GoPro's brain, the processor, can interpret the exact levels of light that the lens initially captured. Like previously mentioned, the processor is the most important part of the system, as it ties together all of the hardware with software algorithms. The embedded engineers at GoPro chose and programmed a processor that can accomplish their industry-leading video stabilization, logging the high-quality video to the camera's memory, and many more tasks never seen by the user. Seeing as the processor is the integral core of the entire system and is extremely challenging to aptly control, most of the embedded engineer's time and effort goes into the planning, programming, and debugging right here in the processor, which leads us right into the perfected software of the system. From configuring the start button to the fast image processing algorithms, each and every algorithm has been decidedly chosen to optimize the camera for maximum performance, cutting out any operations that aren't absolutely necessary to the success of the device. Without an immaculate attention to detail among these tens of thousands of lines of code, there is no chance of GoPro being the industry giant that it is today. Can you imagine the struggles of fitting a world-class camera, ready to take a beating and get thrashed underwater, in a case not much bigger than a golf ball? It's astonishing that the camera has more than a few minutes of battery life for all the tough constraints it has. This has all thanks to the meticulously optimized hardware and software that embedded engineers spent so many hours to perfect. This is why GoPro is worth hundreds of millions of dollars and has been critically acclaimed for years.
So I hope this gives you some sense of what embedded systems are with the GoPro example, and sort of highlights the challenges of actually writing software for such a system. So you could see that in the case of a GoPro, you're required to build like a very tiny unit, like place a world class camera in a very like tiny casing, tiny unit, which needs to be robust and sustain like tough environmental conditions. And they have a lens, and you have optical signal, which is light coming through the lens, and then it gets converted to an electrical signal with this CCD device, and it gets activated based on how much light is hitting it. And then that signal is continuous, it's analog, so it needs to be converted to a digital discrete signal, and that signal is then calibrated to capture whatever you want, like the image intensity, and then that goes through image processing algorithms, which will compute things you need or show you things you want, and that's sent to your phones, and there's this loop, right? So this entire software has to run with computing power just from that device in really difficult conditions. So that software really needs to be optimized based on the computing power it has. You don't have a lot of computing power. It's not like you've been given a data set and you have hundreds of GPUs. Everything needs to work, and this system shouldn't break under extreme conditions. The same is true for our IMU sensors. You might be doing really great sports movements, like you might place the IMU on top of a cricket bat, and then you hit it with a ball coming at a speed of 150 kilometers per hour, or it might be placed on like a military aircraft. So the same sort of challenges are true for our IMU sensor system. So what is our IMU sensor system? I'll talk a little bit about it, and then we'll walk through these slides by Professor Rachel Vitale, who is an assistant professor at the University of Iowa's Mechanical Engineering Department. So our IMU sensor is again a very, very tiny box which is placed on an object which is moving through space. And you can think about it as it's abstracted as a spring mass system that detects mechanical forces. So as it's moving through, this spring is accelerating and it's in a case which might be rotating. So it senses these mechanical forces. And there is a piezoelectric converter, meaning a device which converts mechanical signals to electrical signals, converts it to electrical charges which move through the circuit in form of like electrical current. But this current is continuous. It's an analog signal, so it needs to be converted to a discrete or digital signal, and then this is calibrated with whatever quantity of interest you want to measure, which is known, like acceleration or angular velocity. You might put it on an object which rotates at a known angular velocity, so you know the electrical current signal, you know the angular velocity, you can calibrate it. Or you might drop it with a certain acceleration, like acceleration due to gravity, so you know what the acceleration is. You have the electrical current, you can have a calibration model. and then you actually get readings. So that being said, we can actually walk through some slides of Professor Vitali's on IMU sensors, and that'll give you a better sense of what IMU sensors really are. And you can think about this GoPro example at the back of your mind to relate things. So the thing is, we'll talk about what an IMU is, what it measures, a little bit about the sensor characteristics, how you calibrate it, typical errors, and this problem of extracting like orientation estimates, and what happens if you have more than one sensors and how do you synchronize them. So what is an IMU, right? So these are some examples of IMU. The top left one, XSense MTW. So XSense is Movella. That was the old name for Movella, and it's like, as you see right at the top, one of the best sensors in this field. So this is based on the laws of physics. You care about detecting mechanical forces indirectly. So you're measuring movement, and these mechanical forces are converted to electrical signals. And the simplest configuration consists of this sensor which has three axes, and you measure three components of acceleration in a local frame attached to the body, and three components of angular velocity about these axes, again in that local body fixed frame. And then we have an embedded system, an onboard microprocessor which processes all this data, and then it's streamed to transceiver phone wirelessly. And it could also be wired like back in the old days, but now everything is wireless. And companies like Movella, Xsense have everything really great and wireless. So you measure acceleration. So you see, here you have this case, and there's a spring and there's a mass, and there are these capacitor plates, right? So in this case, like if you accelerate, you see that it's going to change its position with respect to the capacitive plates, and the capacitance changes. There's charges moving through, fluxes changing, and there's an electrical signal generated which we'll then later calibrate. But the point is that there's a mechanical force due to the acceleration on this casing. The spring mass system is activated, and that's connected to this like electrical or piezoelectric system. So there is like change in like the electrical state, like the charge and current, which is then generates an electrical signal. For the gyroscope, you're actually interested in measuring the angular velocity. So what happens is you have this spring mass system in a casing placed on an object which rotates, and as this rotates in this local rotating frame, there's a force called the Coriolis force, which is axial, and the Coriolis force depends on the angular velocity, and that is going to mean that you have a force proportional to the angular velocity which excites vibrations in the spring mass system. And again, there are capacitive plates, which means this oscillating spring mass system is going to interact with an electrical system where the oscillations leads to a change in the electrical state, charges, and thereby fluxes and currents. And then you can actually measure the angular velocity through calibrating the electrical signal. There are also additional sensors on board which help in providing better estimates for where this is located in space. One of these popular sensors is called a magnetometer, which measures the strength of the Earth's magnetic field locally. So it's effectively like a compass on board, electronic compass. And then you might have other sensors like barometer, which measures pressure, and it'll tell you what altitude you're at, thermometers, which measures temperature, as everyone knows. And the thing is, the sensor characteristics might change your temperature, so it's handy to have a thermometer on board. And then you're interested in position, so you need a GPS. But a GPS is not always reliable when you have covers, or if you're indoors, or if you're in a tunnel or something. So you need other sensors, right? So let us talk a little bit about sensor characteristics. So you have something called a dynamic range. So what this means is that your sensor cannot always sense all forces. It only senses forces within a certain range. So think about your human hearing, right? You don't hear all sounds. You hear sounds only within a certain band of frequencies, right? And beyond a certain frequency range, you just don't hear things. So in the same way, the sensor only senses forces, mechanical forces within a certain range. And that range is called a dynamic range. And again, you're making measurements, and those measurements don't necessarily always reflect the true value. So there's an uncertainty due to the measurement, which we call noise. You could also be measuring a quantity which is offset from the true quantity by a known, not a known, but by a fixed amount. So that's called an offset. So it's unlike noise, which is random and uncertain. This is like a fixed offset. And things might change with temperature as well, especially for the gyroscopes. And remember, we get data discretely. There's digital discrete sampling, and there's a sampling rate associated with it. So we'll have a few pictures to discuss this. So here is a signal from an IMU, an accelerometer signal, and this is the range. That green thing is the range. That is the dynamic range. So it senses things inside this range. Now here you have another picture where I think it's an IMU placed on a table, and you have almost like a constant reading, but these jitters, and those jitters tell you there's an uncertainty about a constant value, and that is indicative of the noise. And it's also offset from this value of 9.8, so most likely it's placed on a table and it's static and it's sensing only acceleration due to gravity, whose magnitude is 9.8. So you see there's an offset from 9.8 and some uncertainty due to the noise. And then you're always getting it at a fixed rate, like discretized rate, which is spread out uniformly. That's like representative of the sampling rate. And we have another picture here for calibration telling you which axis is aligned with gravity, but we don't really need to get into this figure, so we can skip it. This slide talks about calibration. So I was telling you that usually you have electrical signals which are generated. So this mechanical state is linked to an electrical state because the activation of the spring mass system is also leading to changes in the electrical system because it was coupled to that capacitive plate and the distance d was changing. That's going to lead into the changes in like the charges moving through the system's currents and so on. So the actual electrical output, the actual sensor output is an electrical signal, and the thing you care about might be something like a physical quantity like acceleration, right? Angular velocity. So there's a calibration model where on the x-axis it's the actual electrical signal measured, which is in volts, and then there's a signal you care about. And usually you go and do a test like dropping a sensor where you know the acceleration. So you know what the y-axis values are, you have measured the x, and you can fit a linear model, which is called the calibration model. And these are sensors that are typically calibrated when they are manufactured. So you don't always do the calibration unless you're doing some kind of advanced measurement, which is the sensor can't handle it. So then you might have to calibrate it. And then typically people use like drop tests and gravity and things like that. And one thing is with magnetic meters, like the magnetic fields vary a lot depending on which part of the globe you're in. So that's something you need to think about while calibrating, if you can trust the manufacturer's calibration. And the other thing we spoke about is that these IMUs sense things in a local body fixed frame. So let's just sort of walk through an illustration of that. So here what we see is we have like this cube and you have these three axes. That's like you can think about a room, and you have like three rulers attached to a corner of the room, and you're measuring things with respect to it. That's your world inertial frame, and maybe one of the axes aligns with gravity, and that's like the up, and one aligns with the Earth's magnetic north, that's north, and then the cross product gives you west. But you have an IMU sensor, which is a tiny sensor, and it's moving through, and there's a frame attached to that, and you're describing maybe the orientation and position of this frame, body fixed IMU frame with respect to your world frame. But the view, or what the IMU sensor senses, the accelerations and angular velocity it senses, are in that body fixed frame. That's something we have to bear in mind. So this picture tells you there's a world frame and there's a sensor and there's a body fixed frame, and we're talking about the orientation of this sensor with respect to the world frame and as well as the position. And this is moving around. Okay, so when we say world frame and body fixed frame, that means that the views are different, what is being sensed is different, and we'll walk through a few GIFs which very nicely highlight this. So here is a world frame and there's a cute dog running in the world frame, and you can see that we're actually talking about how the position, not really the orientation of this dog, is changing as it's moving through in the world frame. But if you have a sensor put on the dog, that if you have maybe a GoPro on the dog and the dog is running through, that's going to actually tell you what the dog sees and the accelerations and positions, the acceleration sensed by the dog. That's going to give you a sense of the dog frame. So we'll have a GIF for that. Now you see, now the dog is running in the sea and there's a GoPro attached to it. What the dog senses, the position of other objects with respect to it, the accelerations and stuff is now in the dog frame. So these are two different frames, and our IMU sensors are like they're in the local like frame, like the dog frame. That's something you need to bear in mind. So yeah, the measurements are typically made in fixed frames, and the orientation is can be derived from angular velocity by integrating it. And here are some equations. Yeah, let's actually, yeah. So you can actually integrate the angular rate to get the orientation, but there are some errors because you have noisy data which are integrating. So when you try to fuse sensors, like you try to use the accelerometer, and because it gives you information about the acceleration due to gravity, if that is the dominant acceleration. And the magnetometer gives you information about the Earth's magnetic field. So then you try to sort of fuse that information in some reliable way to get an estimate of how the sensor is oriented in space. So this slide not really relevant. Yeah, I think this is a great slide. So here, as I mentioned, like when you integrate noisy data, like angular velocity, which is measured, you are integrating noisy data, which means you're going to be integrating a bias or an offset. You're going to be integrating uncertain noise, and that leads to something called an integration drift, meaning things will actually start moving away from the true value. And that's something we need to bear in mind. And here we actually have a nice animation showing that. So there's a static cube, but let's say you actually integrate these angular velocities to get a sense of the orientation of the cube. The integration will actually drift from the true value, which means the cube will actually start, even if it's a static cube, it will start moving away, and we'll be able to see that. So you can see like the cube is drifting away from this static cube, and that's an effect of integrating noisy measurements related to angular velocities. And our pin approach, the great thing about our pin approach is that we don't integrate any kind of noisy data. So that's one powerful motivation behind using a physics informed neural network, is that it does not involve any kind of differentiation or integration of noisy sensor data. We did speak about sensor synchronization. So if you have more than one sensors, then the thing is that they might be out of sync, their clocks might be different, and then that leads to problems. But you might want more than one sensor to do like a reliable estimate by fusing information from different sensors to compensate for like the weaknesses of having just one sensor. So one way of doing this is you could have a chair which rotates and a person with more than one sensors, and then they rotate at a known angular velocity, and then you get this data. You see like angular velocity signals, and you see them from two different IMUs. So they're shifted in time because things are not synchronized. So if you're going to use more than one sensor to sort of do a sensor fusion to reliably estimate some quantity you didn't know, you need to make sure that they're synced. So in our pin example, we don't care about this, but this is a common problem with sensors, is that first thing is when your packets arrive, they need to arrive in the right sequence. And if you have more than one sensors, they need to be synced. So you need to do a synchronization protocol. Something to keep in mind if you work with sensors and hardware and stuff. Just thinking about how pins fit into the broader picture, it's good to have a holistic overview of how these sensors behave. So in summary, IMUs are a great technology. They're versatile. You can use them outside labs, and there's a lot of code available, and there are a lot of techniques involved, primarily centering around sensor fusion. But that typically means you're integrating and differentiating noisy sensor data. Those approaches might be data driven. So the great thing about pins is you aren't integrating or differentiating noisy sensor data. You're approaching it from a first principles physics approach where you're actually thinking about the physical model governing the system. And then you do have to think about body fixed non-inertial reference frames, ground inertial reference frames, how they relate, because those things will come into picture when you set up the equations of motion for these systems, which are like the physical models, and fuse them with the neural network. And I think if you've studied high school physics, which I'm guessing you would have if you're watching this video, you would have discussed the idea of pseudo force. And pseudo force is a fictitious force in a non-inertial accelerating reference frame. So when you are dealing with non-inertial reference frames, you have to be careful about setting up your equation of motion, which in our case we'll be calling the physical model for the accelerometer or the gyroscope. So that's something to bear in mind. The other thing to bear in mind is that these sensors have all these characteristics which you need to know if you're using a data-driven approach, and you integrate and differentiate noise. And with our physics-first approach with pins, that's not really a big concern. So that's another really great motivator for using pins in this case. Apart from the fact that pins are very versatile, and this is a very interesting, unique use case. So great. And now that we have discussed this, we'll proceed to our next item. So again, we need to think about how pins fit in to the big picture, and we have discussed a bit about embedded systems and about the company and IMU sensors and the problem that we would like to solve. But there are going to be challenges when you tackle a real world problem when you think about the systems engineering perspective, meaning that we actually want to set up a pin for an embedded system. And there are these real world problems where you have an IMU sensor which is going to go through an object placed in rugged various terrains for various movements, and those movements might be outside the dynamic range. You might not have a lot of computing power. So we need to think about pins, not just in isolation where you have a great data set and you're working with your computer with Python and JAX and a lot of GPUs, and you're only thinking about the math and fancy NN architectures. Like, that might not be all of it. You might have to think about, can this pin even actually work on an embedded system with all the challenges which come with it? So let us actually walk through another video, a few snippets from a great video on this Engineering Insiders channel, where they do discuss a little bit about the challenges which come with embedded systems.
These engineering adventures start with a ton of questions. Does this processor have enough computing power to run Luigi's Mansion? Will it generate too much heat for the cooling fan to handle and end up burning kids' hands? Which screen is rugged enough to take a good old rage quit, but also quality enough to provide a world-class gaming experience? And once they do find the perfect balance of all of these, they take weeks, months, in some cases years designing and testing circuit boards that are optimized for the application, don't introduce unwanted problems, and fits in a tiny little form factor. But wait, what the heck is firmware? Well, if programming and code is software and the physical electronics and boards are hardware, then firmware must be somewhere between hard and soft, which is exactly it. This middle ground is actually software, but software that is embedded right into the hardware to give it instructions for very low-level operations. But what's the catch? Why is it firmware instead of just software? Good point, but that's not the whole story. Since the software is firmly embedded right into the hardware to stay, It's instead called firmware. Anyways, bringing it back to the embedded world, the firmware role works on the lowest level on the software stack as it interacts directly with the hardware. This could be writing instructions for booting our processor and other hardware, converting the button and joystick sensor signals to digital data for the processor to interpret, managing the communication protocols between each piece of hardware, or any other low-level software tasks. Now,
Okay, so we watched a few snippets of those two videos. So it might have felt like the second snippet was a little discontinued or removed from our discussion. But the reason brought that snippet up is it was talking about firmware, which is there's also very low level software which is fixed and firm and actually runs on the hardware to just boot the system up. And they were talking about different devices communicating. So something we spoke about in the slides, sensor synchronization, and the fact that you need to convert an analog signal to a digital discrete signal. So there's a lot which just goes into that level of the embedded system, which means that there's going to be data coming in, which needs, the first thing is, even for the data to be coming in, the sensors need to be switched on, for which it needs to have good firmware so that they switch on and switch off. And once they switch on, we need the data packets coming in and in the right order. So what if you have the packets at 2 seconds coming in after the packet at 3 seconds, and the packets all scrambled up, right? Or if the sensors are not synchronized properly, or if they're not discretized and sampled properly. It's like maybe there's 0.1, 0.2, and there's a sudden jump to 0.5. So what if you have firmware which is not properly optimized, or you might be doing a difficult movement for which your firmware isn't able to handle these very basic challenges, right? And throw computing power into all of this. What if you have low computing power movements where your data isn't coming in at the right time, the timestamp which is later comes in before, the sampling rate is non-uniform. So there are all these hardware level challenges which, when you're thinking about pins in our little bubble, we might not think about this. So some of the questions we might want to think about are, can pins even handle scrambled timestamps? Can pin handle like irregular sampling in relation to like these firmware challenges? So the great thing about pins as opposed to standard data-driven techniques is that pins does not care about the timestamps. You can scramble them up and pins can handle it. It can handle irregular sampling, which is something very great about it. And it relates to this real world, big picture, low level firmware challenge. So that's great. But the thing is, we're going to be discussing pins written up in JAX. And JAX is very powerful, at least on our CPUs and GPUs. But the question is, can JAX, a library like JAX, even be run an embedded system like an IMU sensor? So that's something which needs to be explored. But let us say it can. Then the thing is, with an embedded system which is going to be exposed to so many rugged terrains in such a tiny box and mass produced, you're going to always run into issues with computing power. You're not going to have all the computing power you need. So can pins actually survive with low computing power? And when we think about computing power, there are two things to it, right? There is the actual optimization engine which works when you keep changing the weights and biases or the parameters of a neural network to learn things, a training process. And there's the memory required to store all those weights and biases to do an inference, and then there's the inference process. So with pins, they work differently from typical neural networks, where the inference is much easier to do. It's not like you have a huge bunch of weights and biases trained on a huge amount of data, and then you have to rerun a forward pass through it. It's relatively light, so we don't have to worry too much about the inference. But the things we do need to worry about is the memory required to hold the weights and the biases, and the number of computations required to do the backpropagation or the training. So what we could think about, some ideas we could think about is, firstly, in regards to backpropagation, if we could optimize the initialization process, meaning JAX uses random initialization, But what if you could run a pin offline for a few different scenarios, look at the trained weights, and maybe see a pattern that, oh, our weights actually live in a certain subspace in the big weights parameter space, and then actually constrain our pins on the embedded system to that subspace. So then we're actually living in a smaller space and doing a few iterations. So that's going to save memory, and that's going to mean fewer iterations to get to your solution. So that is like thinking about optimizing the actual initialization process by gaining insights through offline training. Then another thing we could do is actually use a maybe a compression block where you compress your features. So again, we'll need insights gained through offline training, but maybe you could actually compress your signal to a latent space with smaller, like a fewer dimensions, and then actually project your physical model into that latent space, assuming that it is invariant under that projection. Run the pin there, and then rerun your solution through the compression block in reverse. That could be an idea. What else could we do? Pins are great with sparse data, so we could throw sparse data at it on the embedded system. And there's another technique called next generation reservoir computing, which is a ML technique for dynamical systems, where you actually want to run things with lower power on like IMU sensors for aircrafts and things. So that might be another idea. But these are all ideas I have, and we would need a proof of concept even before we can make any further statements on using pins on embedded systems. Um, but these are just some ideas, and if you have any ideas, just throw them down in the comments. So these are like things we actually need to keep about or bear in mind when you think about pins from a real world perspective and how they relate to embedded systems. And that being said, there's another thing we need to touch upon, which is we spoke about jacks on embedded system, but what is the actual conventional tool to use for embedded system programming? And that will be the next topic we need to talk about. So let us talk about the actual conventional tool for embedded systems. And the go-to language is not Python or not JAX in Python, but it's C++. And that is because C++ is a compiled language, whereas Python is an interpreted language. And I'm going to explain this to you using a fun story, which was an image generated by DAL-E for me. So I am all for gender inclusivity and diversity as well. But the thing is, like, DALL-E generated this image and it was a real pain trying to keep on iterating. So we have white males shown here, but I didn't really want that, but I'm just putting it out there in case anyone has strong opinions on it, just a disclaimer. But anyways, let's getting back to the point. So here, what we see is that we have this image and there are these three people shown. So the first window is about C++, the middle window is about Python, and the last one is about JAX. So think about this scenario. You, as a person, have a friend who lives in another country, speaks a different language, and you want to talk to them. So let's say you actually knew their language, which was really difficult for you to learn, but you took the effort to learn that language. But it's obviously easier for you to think in your language. So you think in your language, you think about what you want to say to this person, and then the next step is you're going to write a nice letter for this person and send it. But you know their language, so you write a letter in their language and send it. So when they get it, they're able to read it in their language. So it's difficult for you because you have to write that letter in their language, but you have gone through that process to master their language. So it's more effective, and as soon as they get it, they can read it and they know what you're talking about. And the other thing you might do is you might have a phone call and you might have a translator, and then you say a sentence in your language, the translator translates it to their language, then the other person hears it, they say something, the translator translates it back to your language, you get the message, and then you have this process which is like a big overload because you have a translator and it's translating line by line. So the first case, where is C++ is compiled. So you compiled a letter in their language and sent it through, and it was there was no interpretation involved. You just were able to write a letter in their language. So in computer terms, you were able to write a code which is executable in machine language. Like the compiler compiled it in machine language and you were able to execute it. So it's much faster. So for embedded systems, you're thinking about mass production and scaling low power. So C++ gets the compiler executes machine code, and there is none of this interpretation from a high level abstraction to low level machine code. That's why it's effective, and that's why C++ is traditionally used for embedded systems. With Python, it's like you speaking your own language. So it's much more user friendly, it's a higher level abstraction, but there is a process of interpretation from like the nice user friendly code you write to machine code, and that needs to be translated line by line in real time, which is really slow because of this interpretation overload. So there is an interpretation from the actual high level language to machine code, and that's why Python is an interpreted language, and it is much slower than C++, which is why it is not typically used to write production level code for embedded systems. Now, we are using JAX, and I don't know if JAX has been used for embedded systems, but JAX is amazing because it has something called just-in-time compiler. So now let's again think about our analogy, right? Let's say you have a superhero translator with this big halo glowing. Now you pick up your phone and you're talking in real time in your language, but this person initially he does this slow translation, translate it and gives a message, but he catches on very quickly, and then he has his magic superpower to translate things in real time without the burden of translation. That is what a just-in-time compiler is. You are writing code in a high-level language, but like a little into that process, your just-in-time compiler is able to actually, in the moment, in real time, compile that machine code and run it. And that's why it's an in between. It's a bridge, or it's an in between, not a bridge, but it's an in between from compiled and interpreted languages. So maybe JAX with its just-in-time compiler, maybe it can be run on embedded systems, and it's something to be explored, which is what we're using JAX with for our mini series here. But that's the conventional tool of the trade, which is C++. And Python is typically used when you have a lot of GPUs for data science. So something to bear in mind. So we spoke about the traditional tool of the trade. Then there's also the traditional technique of the trade for embedded systems. And that is the Kalman filter. So we'll be very, very briefly talking about the very high level picture of Kalman filter, again using a DALL-E generated image. And here it is. So like, what is a Kalman filter? Kalman filter is just a technique for sensor fusion. So we said that every sensor has noisy data. It might not be reliable in itself. So you take a bunch of sensors and you combine them in some reliable way to estimate a quantity which you cannot directly measure, called the hidden state. So here we have these really cute animals. So we have this cute rabbit. His name is Cal. Okay, that's like a funny play of words, like Kalman, Cal. And we have this very cute owl, and the owl's name is Sharp. And we have this rabbit, tiny squirrel. Squirrel's name is Fuzzy. Now this rabbit is always interested in eating very, very tasty carrots in the forest. But this forest is very, very foggy, and it's hard to navigate. So that's like having a sweet seat of noisy sensor data, and you're trying to like actually estimate something. So he builds a very smart map, and this smart map is actually going to tell it how to reliably move to the most tasty carrots. But the thing is, to make this smart map, suppose he listens to Fuzzy the squirrel. Fuzzy the squirrel tells it very like useful things, but it's just like its name, it's very fuzzy. So you can maybe trust it in the long run, but in the short run, it's hard to trust Fuzzy. Or maybe in the short run you can trust Fuzzy, but if the carrot is a little far away, you can't trust it because fuzzy like fuzzies gives you fuzzy estimates. The sharp, the owl can, go up on the tree, has very sharp vision, can look in a longer range, and you can trust it more when you're thinking about longer term estimates. But in the short run, like it's hard for even sharp to know. But you do trust sharp more in general and trust fuzzy less. But fuzzy does give you information to take short steps which sharp cannot, and sharp does give you more reliable estimates, and for longer places it does give you more reliable estimates. So you want to somehow combine the input from fuzzy and sharp with more emphasis on sharp's input. So that's what Cal the rabbit does to make this smart map, which gives it a tells you the positions of these tasty carrots which otherwise are not known. It's like a hidden unknown state which you cannot directly measure. And the only information it has is vision measurements from sharp and clues by fuzzy about short term, maybe displacement steps. So that is what a Kalman filter does at a very, very high story level, just the inspiration. You have more than one sensor and you trust maybe one sensor more or less than the other, and you have to fuse the information from this in some way to get a reliable estimate about a state you don't know, but something that you care about. And that's typically used. And it does work on embedded systems. So that is the idea of the traditional conventional technique, but the actual math and everything is out of the scope, and we won't be discussing it here, and we'll be focusing on pins. And Kalman filter, I guess, does use integrating noisy things from the data, whereas pins don't do that. Yeah, so I guess a few closing remarks. So this was just an introductory video to tell you more about this mini series on pin for wearables and the actual problem at hand, how it fits into the bigger picture of embedded systems and real world challenges, and a little about this company, which is a world leader in this space, this great industry, building these sensors, about our IMU sensor problem statement, a little about IMU sensors, and if this mini series is the right fit for you. Right? So I hope this video has given you a holistic perspective and you enjoyed it, and we'll see you in the next video. Thank you. Peace.